What's going on, you guys? So today we're going to do factorial trailing zeros. So we're given an integer n, we return the number of trailing zeros in n factorial. So the follow-up would be, could you write a solution that works in logarithmic time? So let's try and get a naive solution first, and we'll think about the update. So let's do some examples here. Okay, so let's do that in our text editor. Okay, so we've got 1 factorial, right? That just equals 1. How many trailing zeros are there? 0. Okay, what about 2 factorial? Equals 1 times 2, which equals 2. And there are 0 trailing zeros. 3, 1 times 2 times 3, which equals 6. There is 0. And we can do 4, and then 5 will finally get 1. Oop. Okay. Times 520. Okay, so there's 1 now. So finally we get our first trailing 0, 1. And okay, so first thing I'm noticing is that trailing zeros, number of trailing zeros equals factors of 10, right? Because, for example, 120 equals 12 times 10. So it has 1 factor of 10 and also 1 trailing 0. So the number of trailing zeros is equal to the factors of 10. But also 10 equals 2 times 5. Okay, right? So 5 and 2. So everywhere we have a 2 and 5 combo, we're going to get a trailing 0. Okay. Let's do a few more. 6 times 6. This is 720. Wait, 600. Yeah, 720. So also 1 trailing 0. So 6. 7. Let's do 7. 7. So we're not seeing, so there's 1, 2, and 5 combo in this, so there's only 1 trailing 0. So we're not going to get another 5 until we get to 10. So 10 factorial equals we add 8, 9, 10, and this equals, it doesn't really matter what that equals. So how many trailing zeros? Well, there's 1 factor of 10, there's 2 factors of 10, because we have 1, 10, and 1, 2, and 5 combo. So it looks like, so the number of trailing zeros equals the number of factors of 5. Why is that? Because whenever we have a 5 and a 2, we'll have a 10, which is a trailing 0. There are less 5s than there are 2s in every factorial because there's at least 1 2 in every single even number. So if we have a 5 but we don't have a 2, we can grab a 2 from the next closest even number. Let me give you an example of that. Let's say like 25 factorial. 25 factorial it's going to end up being 1 times, a bunch of stuff times 25, which equals 5 times 5. So you need to grab two 2's from its neighbors to make a factor of 10. So 24, we can grab two 2's from 24, because 24 equals 2 times 2 times 6. And so we can just grab a 2 from a neighbor. So the number of 5's will tell us the number of trailing zeros. So the question is, how can we find the number of 5's in n factorial, in 25 factorial, for example? Okay, so (10 factorial, there are 2. So there's going to be a 5 whenever there's a multiple of 5. So 5 and in 10. How many 5's are there in 10 factorial? 2. Okay, so 10 divided by 2 is, or 10 divided by 5 is 2. Okay, so there's something. So n divided by 5. What does that tell us? Okay, let's do some examples. 1 divided by 5 equals 0. 2, 3, 4, and 5. 5 is 1. 4 is 0. 3 is 0. 2 is 0. Okay, what about 10? 10 divided by 2, or 5, equals 2. Okay, what about 25? 25 divided by 5 equals 5. But how many factors? So we saw when we do 25 factorial, we have 2 5's in 25 instead of just 1, right? So when we divide by 5, we grab the first 5, but there's an additional 5 remaining. So how do we get the additional 5? So n divided by 5 plus 1 for when n is 25. But what is 1 equal to? So when 5 divided by 5 is equal to 1, so 25 divided by 5 plus 5 divided by 5 equals 6. And 6 is the number of trailing zeros in 25 factorial. Right? Because we do 25 divided by 5, so that's 5, plus the additional 5 that happens whenever we have a power of 5, right? 5 to the 0 is 1. 5 to the 0 is 1. 5 to the 1 is 5. 5 squared is 25. So there's 2 5's. There's 2 5's. Well, there's n 5's. 5 to the n, there will be n 5's. So 25, 125 factorial. So there's the 125 factorial. 125 equals 5. So 1 times a bunch of numbers times 125. All right, let's move this down there. Okay. And 125 equals 5 times 5 times 5. So there's 3 numbers there. So if we do divide by 5, we grab the first 5, but then there's 2 remaining. So how do we get the 2 remaining? Okay, so this is 25, trailing zeros. (25) equals that. Okay, and oops. Okay, so 125 divided by 5 plus. So 125 divided by 5 is 25. 25 divided by 5 is 5. 5 divided by 5 is 1. 1 divided by 5 is 0. Okay. 125 divided by 5, 25 plus 25 over 5 plus 5 30 plus 1, so 31. So there should be 31 trailing zeros for 125. And what is that formula? It's n over 5 plus trailing zeros n over 5. Right? Let's do an example. Let's do 125. Trailing zeros. Let's do 25. Trailing zeros 25 equals 25 over 5 plus okay, so what does that equal? 5 plus trailing zeros of 5, and this equals 1 plus trailing zeros of 5 divided by 5, which is 1. And trailing zeros of 1 equals 1 divided by 5 plus trailing zeros of 1 divided by 5, which is 0. So okay, so let's try this formula that we got by just doing the grunt work, just doing it out by hand and seeing if we can see anything, any patterns, and noticing these characteristics. Okay, so let's try that. So return n over 5 plus trailing zeros n over 5. And what happens if n equals 0? If n equals 0, return 0. Okay, let's try that. Okay, so that's the recursive solution. Let's think about runtime and space complexity. So runtime, it's going to call trailing zeros on something equivalent to log n times. It's less than log n, a bit less than log n, but maybe log n as n approaches infinity. If anybody knows how to differentiate between like in binary search, you divide by 2 every time, so that's log n. But when you divide by 5 every time, how would you tell the difference in runtime? Let me know in the comments if you know that. And then space complexity, so we're going to have to call trailing zeros log n times. So it should be log n space complexity. Time complexity. So the follow-up question was, could you write a solution that works in logarithmic time complexity? Let's do constant space complexity. So we have logarithmic time complexity. What about logarithmic space complexity? Well, we can convert this to a loop. So what's happening every time we're dividing? Every time we're dividing by 5 and adding to a sum, right? We add n divided by 5 to our sum every time. And then when we get 0, we return. Okay, so while something is greater than 0, keep going. And then after we equal 0, we're going to return, let's call it zeros. So we'll make a variable called zeros, set it equal to 0, and we need to make a writable variable, we'll call it remainder. We'll set it equal to n. We'll say while remainder is greater than 0, we'll add remainder divided by 5 to zeros, and reduce remainder to itself divided by 5. So slash equals, this is equivalent to saying the following. Just have to write a little bit less. Okay. Let's see if this works. And so this should be, so we're running through this in log n times. We're only saving these two int variables, so it's constant space. So recursive, iterative, okay, so let's run this, let's see what happens. Okay, you guys, so there's a log n time complexity of 1 space complexity solution for you. Yeah, stay tuned for the next one. See you guys.